So we want to talk about, my name is Dean Hildebrand, and it's been work with several other people between both of our companies, and I want to talk a bit about what we're doing as a partnership between DDN and Google. So I work in the CTO office at Google and defining its file storage strategy as we move forward for HPC and enterprise and the rest of it. All right, so I don't think it's too much of a surprise when you look around. There's a bit of cloud discussions going on. There's definitely a lot of interest. I think the questions, that I want to address here is around, what are the challenges? What are the difficulties? How can we help, more or less? And so in HPC and the cloud, we can see that the interest is growing, the use is growing, but it's a little sometimes unclear on which areas are being successful, where the problem pain points are still, and so let's go through that. So at Google, we love HPC. We work with many of these industries already across a variety of different methods, either through ads, through G Suite that they use in their organizations, or in many of the ones such as, actually, all of them, we already have existing customers that do one thing or another inside our cloud, from data warehousing to just quant analytics in the financial services area, and many others. And so the thing is, the ones that have been successful until this point have really figured out a way to become cloud native, if you will. And I don't like using that term, but it's like a term where they can figure out the object store and our compute infrastructure and BigQuery and the rest. And I think that has limited us in terms of a fintech company using us to some degree, but then the rest of the workloads have to stay on-prem, or they lack the ability to burst out parts of their workloads. And so that's where our partnership with DDN is to really extend that reach from on-prem and into the cloud and get the rest of those workloads into Google. And again, the goal here is not to replace on-prem necessarily, but to build an infrastructure in a hybrid cloud way where we can solve a lot of the on-prem difficulties, right? I mean, when your queuing ability and the amount you can compute is there and your desire is beyond that, you're just missing out, right? You want to go faster than you can and you can't figure out how to do it. On the other side, when there's a dip and the queue gets shorter, all of a sudden, now it's just wasted money. Your servers are up and running. Nobody likes to shut everything down, and you're just sitting there idle, and then that's money out the door as well, right? Everyone wants to keep everything hot all the time, because otherwise, how is your investment getting its return? And so, but when you take those workloads that are running on-prem, there's a lot of challenges when you're moving them into the cloud, right? We have, sorry, I don't have the screen on my side. So a lot of times you didn't write the code yourself, so you don't even have the opportunity to rewrite it to use a different storage system or just refactor the algorithms. And in many cases, researchers and the people that are running the jobs are very comfortable with the way everything has been laid out. They like the tools, they like the workflow, they like everything it has. So we want to give them something that's familiar, maybe a little bit different, but familiar at least in one way or the other. And we need to get through those barriers before people start really adopting it en masse. And so, again, we want to take advantage of the benefits, and that's where we're here today. But, the complexity, sometimes it looks like a big, gray, fuzzy bubble, and you're not really sure what is it and how do I start. Sometimes there's just too many entry points into the cloud, and it's hard to know how to get going. So one partnership we just did with Clemson is around running a job that had 2.1 million CPUs. And I think this is, again, something where on-prem this just wasn't possible. And so the team at Clemson was really starting to think about what could we achieve if we had X amount of unlimited compute. And so then for them, they said, well, we think that there's an area around aiding first responders in context of a disaster. So let's analyze video feeds, see if we can give real-time updates to direct traffic, let's say if they wanted to evacuate a city in real time. And so in order to do that, they took 3 hours and they scaled up to 2.1 million vCPUs, all sharing a single 211 data set that consisted of 2 million hours of traffic videos. And so this, this wasn't, plug and play. This took a lot of work in order how they were going to make this happen. But this is something, again, where we're just starting to see these huge, massive jobs where they have to leverage multiple regions, multiple zones to really make it all work. But the storage infrastructure and the compute infrastructure is there. And so we just need to figure out how to make it happen, right? And I think these types of use cases are really paving the way for the smaller ones that don't need such scale. But they also did it in a cost-effective way where, for example, they're using our preemptible instances, which is really just filling in the set of VMs that aren't being used by everyone else. And then by doing that, you get an 80% discount on the VMs. And that's a fixed price at any time of day. So you can really plan out your budgeting in terms of how much compute you're going to use. And now, preemptibles are not guaranteed to happen, but as you can see, without sort of any fancy background shenanigans, you can scale up to 2.1 million within 3 hours. So there's enough around that, for whatever you're looking for, you can make use of that, right? So lots of clouds. What makes Google different? I think there's a couple different areas around. I mean, we'll talk about the technology. We'll talk about the awesome partnerships with DDN. But at the same time, I think there's a lot of just how working with Google operates, right? We treat open source and all of the projects that we've been working with, Kubernetes, TensorFlow, these are first-class citizens within the company, within our cloud as well. And so we put a lot of time and effort into those areas. And by working with us, you're really working with the researchers that are developing these projects. Another example is hybrid and multi-cloud. So we, as I said before, really see this as the end state, or at least the next X number of years into the future, 10, 20 years, or however far you want to look forward. So we really need to plan the software around how does multiple clouds work, how does hybrid cloud work, and we can't just assume that it's going to be one cloud, and so all the tools we give you just operate within the one cloud bubble. And so that's something, again, that really is a core to the products that we're delivering and the roadmaps that we're looking forward. And of course, AI and ML, right? I mean, that's clear in Google's leadership position in this space, but at the same time, we haven't focused the energy on the HPC and the scientific community. And I think you're going to see a lot more collaboration between taking the algorithms that are available out there and applying them to much more very interesting problems such as genomics and healthcare, EDA, simulated. There was one of the papers was around simulating chips. I think all of these types of things are going to happen as we move forward. And so we take the best of those algorithms and make them as services inside Google Cloud. And that's where TPUs and all those types of things are bubbling up to the surface. So I think I'm going to skip over. I mean, I could give an overview, but it's not really the topic today of everything on Google. Please see me if you want to find more about just the general compute options. So on the storage side, though, we're going to start off with something that looks like this. Maybe you have one data center or you have multiple, but your data centers are going to have to figure out a way to hook them into some region, maybe multiple regions in the cloud, and again, maybe multiple cloud vendors. So once you have that up and running, though, how do you make it all work together? And there's a lot of choices you have to make when you're doing that process, right? Is it going to be more of a lift and shift, a lift and improve? Or are you just going to rewrite certain algorithms to take advantage of different managed services that are in the cloud? How much queuing do you want to do versus real-time just spinning up more VMs? I mean, it's more cost, but you can get more done. So you have to really decide on what is the budget that you want to spend, and then how much science per second do you want to achieve with that budget is really, I think, one of the key things to understand as you take advantage of the resources. So a few different models that we're seeing, and I think this relates again to storage and how you're transferring storage around. In the launch model, you're doing a lot of work on your laptop, let's say running MATLAB, but then you want to burst out a MATLAB job into the cloud. Good, and it's really useful, except on the other side, if you have a lot of data, this becomes pretty challenging. How are you going to move that data back and forth to really make it feel like a real-time experience? The burst by type, what I like to do there is you can take Slurm and you create multiple queues. On-prem, one of those queues heads to your existing cluster, and the other one will automatically launch up into the cloud and auto-scale VMs inside of Google Cloud as needed. And so in that model, you can pre-stage all of the data up into the file system or the object store or whatever you're using. And so you can really get this feel where they're both working together, as long as you realize that the data, primary copy for data is here, and for the one in the cloud, and the other one's down on-prem. And then you got the all-in model, which again, we're seeing, I think there's a lot of new students and industries, even scientific ones, being born in the cloud, and so we're seeing some of that, but I would say in general, right, we're seeing much more of that hybrid model. So, and I think when you move into the cloud, one of the keys is, as I say here, embrace the application differences, meaning if your applications have different storage workloads, some of them have IOPS, some of them need bandwidth, don't deploy a single file system for all of them. You really need to, I think about what kind of storage do you have, or what kind of app do you have, what kind of storage you're deploying, to try to tailor the storage for your workload. The idea that you can just take a huge system and then bin pack everything together and then have all your workloads fight, it doesn't seem to be necessary anymore in the cloud. I mean, you need to bundle them up into data sets in terms of the workloads that access certain data sets, but if you can split apart your data sets, you're probably going to have different I/O workload patterns between them. So why wouldn't you tailor your file system to meet those needs? So I think I'm going to skip through that. So let's talk about DDN. So DDN has their version of Lustre inside the GCP marketplace. You can go to the marketplace, click a few buttons and hit go, and I'll spin that up for you. So we've tried to make it easy. They provide support for that instance and everything else. Let's see. But what I wanted to talk about is we've also worked with DDN on submitting a few IO500 runs. So I just realized I probably should have put in a slide for IO500. So who here actually knows what the IO500 is? Someone was on the talking. That guy over there knows. No one else. Okay, so let me explain what it is. Essentially, we have the top 500, which rates the largest supercomputers in the world. What we're trying to do is something on the storage side that does something similar. And by similar, what I mean is, how do you compare and evaluate all the different storage systems that are out there in the world? So we have different sets of file systems, but then we have many different sets of disks and SSD and networks. And now with cloud vendors coming in, we also have a whole different way of configuring things inside the cloud. So what the IO500 did is compile a set of standard benchmarks using IOR, MD-Test, and a few others that everyone agrees, at the minimum, these are types of workloads that we see on-prem. And what it does is evaluate best case scenarios and worst case scenarios. Everyone likes to know what it can do in the best case, but then a lot of times you care about that worst case as well, because you always got that one researcher who's doing the worst IO workload possible. So you want to know what they are, and that's where the benchmark is meant to give you a fully complete picture from the best to the worst. So we ran 3 different versions, configurations of Lustre with DDN in Google. One was done a year ago, and now we did another 2 this time around. So you'll see they revamped the list, so there's 2 on the list at the moment. But we tried to make them very different and using configurations that we're seeing from our customers. But on the upside, you can see, depending on which one you choose, we got up to about 107 gigabytes per second. And so if you think about that as access to a single data set, not in terms of access to a single storage system, I think it really ends up being a pretty decent number, because generally you need bigger when you're having many users access many data sets. If you can parse out the data sets into IOPS and bandwidth optimized ones, then right now I'd love to talk to you if you need more than that. Because I know we can go bigger. It's more of like, where do you stop, more or less. So looking at the 2 configurations, one was based on our disk-based product called PD Standard Persistent Disk. So it's a persistent storage, but it's all based on disks. And the other one's based on persistent disk based on SSDs, so persistent SSD. They're both persistent, and we just configure the Lustre OSSs and the MDSs to use those 2 types of storage systems. In both of the cases, though, we want the metadata servers to use the SSD ones, right? You want to have responsive interactivity with your file system, and it really doesn't cost that much to throw out. In this case, we used 5 metadata servers and then striped the metadata across all of them. And what's interesting is that the numbers really aren't that different, right? Because at the end of the day, a lot of the numbers end up being in latency, which isn't really measured by the benchmark today, because it's really just about IOPS, and no matter how fast you can get them. So you can always cover up latency with lots of threads. And so that's where you don't really see a lot of the differences here. But then when you add up the scores, they're actually pretty similar. And again, that's because the metadata jobs that are really hitting the metadata servers, they're using the SSDs, and that shows how important the metadata server is generally when you're evaluating your storage system. So one thing I wanted to do then as well is compare, if you take different versions of how we deploy Lustre, what is the different cost models that you could see? And again, this is all depending on what you're looking for your application. So I'm just going to move around to the other side so I can point at them. So we have an Ephemeral Local Ssd product as well. This is a result we submitted last year. So you basically burst it out, it goes super fast, but if a node dies, you lose your data, right? So really good, really fast, but wouldn't use it for critical data. But then, if you have a batch system and you can restart from scratch, then it works great. Then we have our full performance SSD, persistent SSD offering. I created a smaller one that optimizes for bandwidth, not for all of the IOPS that this one has. And so you can see it's a little bit cheaper. And then our disk-based device. And so what's really interesting is if you want to have all the performance, you have a fair amount of cost associated with that, right? Generally, as you would expect. If you get the biggest and best and it's all SSD, it's going to be expensive. What I show here is different discount models that we have for our users that are all just built in default without any negotiation, and how those ones look. And so what I find really interesting in this chart is that if you take there's two really important things, I think. One is the local SSD offering and the disk offering couldn't be more different in terms of their configuration. One's persistent, one's high latency, and one's low latency. Well, let's go medium latency and low latency. And one is really designed for bandwidth with disks, and then one's really designed for IOPS and bandwidth with just local SSDs inside every one of the OSSs. And they end up being the same price, right? But they have very different capacities, and that's something that's not shown in this chart. But for the same price with a disk, you get a huge, massive system, as you can imagine, and always with SSDs, it's going to be smaller. And that's why, again, if you want to pick one system that suits everything here, it's going to cost X. But if you can pick two smaller systems that micro-optimize for your workloads between the full disk and the local SSD, then you can save them. If you split out the cost in half, your cost is about, what is that? A quarter of what the full one is. And you've actually done your jobs a benefit by not having them compete all within the same storage system and to share the amount of IOPS that are in that graph. Does that make sense? Is there any questions on that? Yeah, awesome. I think that's the main bit. And then the rest of it is more DDN-based ones that I can't talk too well to. So that's the main thing I wanted to talk about is, yes, please.
Are you saying by sharing that means like isolating storage, computations? Are you saying that?
I'm saying that, so when you deploy your Lustre, you have to choose a type of storage for your OSSs and your OSTs. So you could either choose a persistent disk-based option, or you could choose a persistent SSD option, or you could choose a ephemeral SSD option. And then each of them give different price-performance trade-offs. Each of them have different capacities for the same price. But in this case, for 1 hour, it takes about an hour to run the IO500 benchmark, costs you here about $100. So you can have a top 10 storage system literally for $100. Yeah, no, please. So this is the cost. So you can just go onto our website. We have a GCP Pricing Calculator, and you can just type in what you need, 100 OSSs, X amount of storage, and it'll just pop out a cost. And so that's what I did here, was taking in the cost for the metadata servers and then taking in the cost for the OSTs and the OSSs, and then just summed it up. Now, of course, this isn't including, maintenance or support costs from DDN or anything like that. But I just wanted to show why it's important to pick up a system and target a specific workload, just because if you choose the full one, hey, that's great if your workload needs it, but possibly all it really needs is high bandwidth. And so, at the end of the day, why not choose the cheaper high bandwidth one?
Or however long.
Oh, okay. So, any other questions on anything at all? Any topic? No?
No.
All right, so please find me here in the booth afterwards, or find me in the Google Cloud booth as well, and thanks for all your time.
Awesome. Give them a round of applause. We love having our guest speakers, right?